And next, let me invite to the stage from Project Numina, co-founder Jia Li and team lead Marina Vinyes.
C'est bon là? Est-ce que là c'est bon? Non, c'est pas bon.
Hello, can you hear us? Great. So hello everyone. Thank you for inviting us. We are Project Numina. My name is Jia. I'm the co-founder of Lumina, and I'm here with our team lead Marina, and we're going to we're going to here to present a bit what we have been doing in this area, and we're going to go very fast about like AI for mathematics, how this evolved very rapidly in last 2 years. And then we're going to focus a bit what we are doing, especially to one of our ongoing projects to evaluate a new generation of AI model for autoformalization. So yeah, most of the 2 minute, two sentence about Lumina. It's a non-profit organization. We're based in Paris. We do open source work to accelerate the development of AI for mathematics. And currently we have a strong focus on lean and formal mathematics. Some numbers we have, it's completely open source. So theoretically, everyone can participate, but we do have a bandwidth issue. We have some, we receive donations, so it's not a startup, it's non-profit. All of our work are supposed to be fully open sourced. We do have access to some compute. Well, at the moment, at a particular moment of last year, we have a lot of H100. We don't have them now, but we do have access to some compute. Some of our famous work are related to dataset and some basic infrastructure that we have released to help people to train model on these areas. We have also trained some models ourselves. And like for example, for the past year, we have been focusing on formalizing Olympiad problems. So that's maybe a bit far from what you are working regarding research mathematics. So again, very quickly, so this is not about lean, but in the it's 1 year and a half ago, when people try to train, let's say AI to solve mathematical problems, it's an area where we use informal mathematics. So we try to, well, today people still use that. So you give the problem in natural language, you expect the model to output a natural language solution, and you find a way to verify them. So one of our first work is to use Python so that the model can reason in natural language and use a Python interpreter to find the solution. And yeah, that's all. And what we have, well, I mean, let's say our first big participation into this area is this AIMO Progress Prize competition organized by HTX Market, who is being also very supportive to the Lean community. So they organized this competition where they asked team to create AI model to solve 50 problems at the style of AIME, which is for each problem you have a final numerical output ranging from 0 to 1,000, and instead of verifying the reasoning trace of the model, you just verify the final answer to see if it is correct. So we have developed a model based on the principle that I just mentioned. You use Python the model use natural language to reason, and then use Python to execute the reasoning, and so to output the final answer. And also at this occasion, we release a relatively large data set, still focusing on high school level competition mathematics. So this is some numbers about our data set. Back the time was the state-of-the-art data set, and along the way, people have released, especially the team of NVIDIA, better data set along the way. But at the time, it was the biggest, and it is still used by quite a lot of people even today. So I mean, the data set that we release, there's some concept. I'm going to spend maybe 1 minute on it. So what is particular at this data set is like, maybe I'm going to spend 1 or 2 minutes for you to understand, because this is highly related to Lean and why the community or all this AI company is certainly interested in Lean. Because to train an AI model, you need, let's say, some verifiable signal. So in the beginning, for mathematics, it's very difficult because it's really hard to verify if a proof is correct. Until like this last 2 or 3 years, people realized there are particular math problem that has a numerical output, so a filling blank problem, and you can use that as a very strong signal to train your model. So instead of verifying if the reasoning trace is correct, you just verify the final output. So at the beginning of this year, you have a model called DeepSeek R1. They use this principle plus what they call reinforcement learning, and this enable the model to do really complicated reasoning to solve a mathematical problem that we cannot imagine, but still in the high school competition level. So why this is linked to Link? Because to Lean, sorry. So if you move on to research level mathematics or more difficult mathematics, it's extremely hard to construct problem or non-trivial problem with numerical or verifiable output. Like for example, the most difficult math problem hypothesis, they are proofs. So you need to find a proof, and there's no final outcome that something can be verified very easily. So in the ideal world, this LLM company, including us, will think that Lean will be the perfect environment for this model to learn and self-play, so that we can create a paradigm where this model could be really, can generate a lot of synthetic data themselves, and could reach a human level reasoning at research level mathematics. So this is like the idea and the common point with the early exploration, let's say 1 or 2 years ago. So this data set is quite important because this is the data set that we release is one of the largest data set where you have a lot of competition level problem with numerical output. So this allows you to do a lot of work. Basically, for example, in the early days, people do what we call rejection sampling. So you have the Queen 2.5 model, which is still widely used today. And then a while after, you got the DeepSeek R1. But what's really impressive is like July last year, you all know, DeepMind released AlphaProof with a silver medal level, so which catch everyone's attention toward formal mathematics. And it is kind of the very first proof of concept that you can combine AI. Well, you have other proof of concept, but this is really shocking. So we all know the story. Well, we all know the story. So it is also at this moment that Lumina say, okay, our team say, okay, informal math, can do a lot of things in competition level mathematics, but if we want to go to research level, probably Lean is the best tool, or formal language, sorry. But the formal languages like Lean could be a potential candidate to help this model to progress toward research level mathematics. So yeah, now Marina will explain a bit what we have been doing this last year.
Yeah, so last year, given this result of AlphaProof, we were focusing on basically reproducing this kind of result, but completely open source, so open data, open model. And the goal for last year was a gold medal for the recent IMO that was in July. So we focused on formal mathematics for everything that Jia explained, but also because of the results of AlphaProof. And our first objective was to collect data on formal mathematics, because there was no like big data set, public data set on this. So we needed pairs of statements and proofs in Lean. And we continued in parallel the effort of increasing the size of our informal data set, because it's still very useful for the community. And also it can feed our formal data set, because as you will see, we start from informal data to go to formal data. So how did we build this data set? So we started from informal statements. So this is a public data set that is called Numina Math 1.5 that you can access in Hugging Face. We excluded combinatorial and geometry problems because they are more difficult to formalize. And we ran our own auto-formalizer model to automatically translate those statements to Lean. And all of these statements were sent to reviewers to verify that the formalization was correct. Once those statements were reviewed, we needed some kind of automation to scale the proof formalization. So what we did is that we used our prover model to find proofs for these statements. And if the proof is found by the model, we could add it to the data set. If it's not, then we had a manual annotation pipeline. And so we had mathematicians working with us to formalize these problems. And one thing that we found out is really sometimes formalizing a proof is really long. It takes a lot of time, even for experts. So, and in terms of efficiency for learning on the large language models, we need a lot of tokens. So basically, the first hour or the first hour and a half, the annotators were building the proof, and then so a lot of tokens, and then after 1 hour and a half, it's complicated to continue constructing the proof. So we were not getting a lot of more tokens. So we were capping the time of at 90 minutes. So some proofs in our data set are not complete. So they will contain some stories, but they are the structure of the proof is there. And yeah, and also sometimes we had the informal proof of the problem. So this could also be used to help the annotations. So we released, as we said, we released a lot of data sets that are widely used. So the ones we released last year was the Numina Math 1.5, which have 1 million problems in informal natural language. And the one that we released in July is Numina Math Lean, that contains 100,000 statements and proofs in Lean. All of this is competition level, so it's not research level mathematics. Is because our goal was really on the IMO. And so, given that data, and we wanted to focus on the formal proofs, because there was a lot of success with AlphaProof. So we looked at what was done what are the approaches that were used. And basically, there were two kinds of approaches. So the step provers, which are combining some proof search, but step by step. And at each step, you use some model for exploration. So, for example, you use DeepSeek or not DeepSeek, but some step prover that will give you the next step of the proof. And this family of approaches, they had quite good results in the benchmarks that were used in AI format, but they were computationally expensive because each step of the proof you need to call inference of a model. So this is quite expensive, and for long proofs, it was becoming very expensive. And so there were another class of solutions that were called whole proof, where the model is generating the whole proof at once. So it's much more computationally efficient, but it was struggling for more complex reasoning and for more complicated problems. So the idea was to see if we could combine the idea was to see if we could take advantages of the computationally efficient, but still do better exploration like the step prover. And this at this time was when the O1 models was released. So it was in September 2024, I think. And basically, these O1 style models, what they did is all the exploration is done in what they call reasoning. So the model is doing some reasoning blocks before giving you the final answer. And so we adapted this to math, and what it means is that we allow the model to think in informal language, so how the proof kind of looks like, and it combines this by outputting different blocks of Lean that can help at the end of the proof. And at the end of all this reasoning, it will output the final Lean code. And this was, so this here you have an example. So you will have some parts that are written in natural language, then some Lean blocks. And this, we found out it worked really well. So once we had this approach, we published a paper and we started scaling, basically. So running with more data, more compute, and we released 2 models. So one in February, the KiminaProver preview, which at the time had state-of-the-art result on the mini F2F benchmark. And we continued scaling, and we released the KiminaProver in July that still had another jump. And we participated to the IMO, but unfortunately we didn't get the gold medal. But what's interesting to see in the results of IMO last year is that compared to the IMO the year before, in this year we had very good results with informal models like Gemini and OpenAI both got a gold medal, and 2 years ago people were thinking that this kind of models could not solve this kind of complex proofs, so it was kind of a surprise. And on the formal side, also there were Harmonic and SeedProver that achieved gold medal, and the SeedProver was using very similar approach to us, but more scaled with more compute. So yeah, and we released a demo with our model where you can input a statement either in informal or either in Lean, and run it to see what's the output of our model. Yeah.
So, I mean, so this was what we have been doing, like, let's say the past year, our adventure on the, let's say, formal mathematics for competition level math. So now the key message is really about, so this mini F2F dataset was like the guiding dataset for the AI formal math, let's say, research for the last 2 or 3 years. And it was one of the most successful benchmark in this area, at least for those who are doing machine learning. It is completely focused on competition math. And you can see that, I mean, when we started in 2021, it's difficult. It's a very difficult benchmark. And then all of a sudden, since last year, things could change very rapidly in this area. So people asking what's next, and of course now you have Harmonic, you have MathIn. They are introducing their new AI model to help you to write lean code. So I think people there are some hope that all this model could actually either help mathematicians in their research work or help you or the whole lean community to formalize more mathematics. So here are some reflection about artificial super intelligence. And we are seeing that informal model is already able to solve, well, I mean, there are many people that think that competition level mathematics are kind of solved by this large language model. But there is still one question that is very important, and that DeepMind is really, and also DeepMind has also proposed a lot of idea and some thought about it, is if we want to have an AI that achieve human or surpass human level performance in mathematics or in general in other science, do we need formal mathematics or not? So the idea is, it's a bit what I say in the beginning, if you don't do formal math, so you stay in the informal world, you have a lot of flexibility, but it's very difficult to verify. The model hallucinate, and like, let's say 1 year ago, we are thinking it's almost impossible to verify until Google released more work suggesting that, okay, if you stay in the informal, you still have way to verify. So that's how they get the gold medal using informal model, which was considered as impossible like 1 or 2 years ago. So on the one hand, if you don't use formal or you stay in the informal, you have more flexibility. You will be able to solve a larger family of problem, but you don't have perfect verification. Now, on the other hand, formal is good because you have a very clear signal of verification, but you rely on Mathlib, and I mean, people from DeepMind, when they build a formal conjecture repo that you will have probably next tomorrow, is saying that there is still a significant gap between what we have in Mathlib and what we want to achieve using this LLM. It's basically well, I mean, at least they consider, we don't have that much compute, but they consider the model is progressing faster than Mathlib, and we should find a way out. So currently, the bottleneck of doing formal mathematics is really the foundation of all the library that we have. It's not as rich as what we can find in the informal world. So what we plan to do at Numina is to, let's say, create the next benchmark to help this model to progress. So the goal is to create a benchmark. Well, it's not only a benchmark, but I'm going to present it as a benchmark. So the idea is to create a benchmark to evaluate 2 things. First is how good a model could be as a lean assistant. So you are writing lean, probably research level mathematics, or at least graduate level mathematics. You want a lean assistant, a model that can be a helpful assistant to help you. So you want to evaluate how good it is. And the other aspect is like, we do not have a human, so we want to do large-scale autoformalization. So is it possible to have a model to do large-scale autoformalization by itself without any human intervention? I think that's a dream of all these companies. So our goal is to try to build this benchmark, and with the help of the community, of course. So our starting point currently is the 1,000 theorem plus that we can find on the internet that give a rough overview of what's already in MathLib and what's not. And so, well, I mean, at least from this list. For example, this one, I think it's not in MathLib yet, or maybe it's already in the last few months. But so this one, at least it's indicated it's not in MathLib on this website. And the way that we formalize it is like we are splitting the main theorem. So you have the formalization of the main theorem, and you have all the lemmas. So within this LiveProveBench project, we took this theorem, we try to formalize them ourselves using AI. So it's I'm going to talk about it later. But so we try to formalize them, and then according to a blueprint. So we have all the lemmas that help us to construct the final theorem. And what we're going to do is to remove all those all the proof, so that we know the statement is correct, at least according to our knowledge. And we're going to give this to a model to evaluate. So there is two modes. So the first mode is we give the model only the main theorem statement. So it's like, let's say, the autoformalization mode. We want to see if the model is able to do a bit, let's say, a long chain of reasoning to get to a non-trivial theorem. The other mode is like the assistant mode. We're giving the model all the intermediate lemmas that help us to construct the final proof. And we ask the model to prove all the lemmas, and then it will be able to use all the lemmas to prove the final theorem. We are not done yet. I think we have like 20-ish theorem formalized. Yeah, the particularity is like within this project, we've both formalized the statement, or at least we want to have as many theorem where we are sure about the statement. So we also formalize the proof together with the statement. It's a bit different, like for example, from Putnam bench where you only have the statement. So for example, we have evaluated one of the IMO gold medal level models that we have access to. And in the assistant mode, it's good. It's good. Well, I mean, it's trained for IMO level problem, but it's able to do lemmas in the 1,000 theorem plus repo. But it's much difficult to ask the model to act on its own to do autoformalization, where we only give the last statement of the theorem. So the goal is really to, well, at least on the benchmark side, to get it ready and to guide all this company to build a helpful assistant for the whole community. Instead of, I mean, people try to, I mean, the goal is really to go beyond competition level mathematics. So yeah, so I was saying that it's not only about a benchmark. So the aspect of the benchmark, I think maybe you are not very interested in. Maybe this is for the company who are developing model, at least formal mathematical models. But on the other hand, the reason we want to formalize, so one way to do it is just to throw out all the statement. But we want to make this, let's say, a small experiment where we have AI and human collaborate together. So when we try to formalize the proof, we require all our contributors to use the AI tool that we built. So the idea is to say, a bit like the previous talk, today AI is helpful, but maybe AI could achieve 20% of the of the lemmas. And but we want maybe there is a future where AI can achieve more and more. So maybe in 1 or 2 years it could be 80%. But it is important to explore how human and some AI tools interact. So within this project, we also build some AI tools to help our contributor, and we force them, unfortunately, to use them to help us to iterate on them. So we developed a bunch of AI tools, which is less generic than what Harmonic or MathInt developed. So it's dedicated. We build some dedicated to help these contributors to formalize this theorem. So one of them, we just released one of them, we posted on Zulib. So, I mean, this, we have really positive feedbacks among our contributors. And when other tools are more mature, we will also release them. So this is a semantic search tool built on the top of LeanDex Pro. Some of you might have used it. So we are grateful for that. But we add a model on the top so that you can really do semantic search by doing natural language. So like, for example, here I am really lazy. I don't even formulate my research. I just give the search engine the text state, and it's able to find the theorem or the theorem in MATLAB that I'm looking for. So it is structured very similar to LeanDex Pro. We are adding more and more packages. So yeah, please try it. Well, I mean, our annotators or our contributors love it. You can also scan the QR code to have access. It's completely free. I think we're going to release the code behind it as well. But yeah, you can just try it, and you don't need to remember anything about the theorem, but everything is in natural language. But yeah, so the idea of what we are trying to explore is first creating a benchmark that help the next generation of AI model to be really helpful for the research or the formal mathematics community. And within this project, we welcome all contributions. So if you have some idea of collaboration, we can do it together. So our goal is to explore within this project how contributors or mathematicians should interact with AI informally or with formal languages, so to speed up their research. And finally, we are releasing all the tools, and probably in 1 or 2 months, the formalization agent that we're using for the whole community. And also, we are also releasing the benchmark once we think it's ready. So I think that's all. Thank you.
Thank you very much, Jia and Marina. Questions? Yes, please.
Hi, thanks for the talk. You said that per step approaches with Monte Carlo tree inference are that they are slow because the model inference is very slow. Could you elaborate a bit exactly why?
Yes, so the model inference is the basically same time for one approach or the other approach, but for Monte Carlo tree search or best first search, you need to call the model sequentially after each decision. And that's what it's, and compared to the whole proof model where you just call the model once and you generate the whole answer. So basically, let's say the number of calls to the model is like the number of tactics that you will have in your proof or something like this. So that's what that's why I'm saying it's more computationally expensive. It's not just one inference.
No, my question was mostly these are all transformer-based models.
Yes, it's the models that we use is LLM, like kind of LLM models. We use the Quen models, Quen math, but yes, transformer models.
But this wouldn't be the case if they were, say, recurrent neural network or stuff like this.
Sorry?
If they were based on recurrent neural network or some other architecture.
A cheaper one, you mean? If
it wouldn't need to scan the entire proof at every step.
I don't know if I got the question, but in the step prover models, you cannot generate the whole proof because you need feedback from the compiler at every step. You generate one step and you put a sorry or something like this. And so you get feedback from the compiler at every step. So I cannot generate the whole. So and you
you update it line by line. That's kind of logic.
Yes.
Okay, but I think this that you wouldn't need to scan the entire state if you were using stuff like, I don't know, recurrent. I don't know. I need to see a bit more detail. So okay, never mind.
Hi, thanks for the talk. So it seems like a lot of the companies working on AI for theorem proving go one of two approaches. So either they do what you've done and use this Monte Carlo tree graph search using actor critic model or something like this, or they do whole proof generation with an LLM. Maybe they feed it some context with MTP tools or something like this. And for me, at least, I don't know what seems more promising. What do you think of the benefits and the drawbacks of each approach? And do you have an opinion on which you think is more promising?
Yeah, it's a bit, the microphone is not working well, but I think I get your question. Correct me if so you are asking if what kind of approach this company are doing? Well, this is the debate, let's say at the beginning of the year. People don't do, I mean, they have a hybrid approach. I believe most of the company, what they're doing is an agentic approach. So today, if you, I don't know if you already have the presentation of the math int, but let me go to the, yeah. So I think maybe Google, they still have this tree search model, but today there's not people do not choose one or another. You just use an agentic framework where you have a model have access to different tools. So it's a bit like Claude if you have used it and someone built a fantastic library called LSP, LeanLSP, something like that. I should give the link, but it's you use Claude code, you provide the model, the Lean compiler and some search tool, and it's able to work in the Lean environment. So most of the companies, so like it's a hybrid approach. So the best reference is SeedProver. So when SeedProver sees a proof, it's going to use a informal reasoning engine. Well, it's its own, but you will have a first part where the model generates the informal reasoning, and then the model will try to write something in code, maybe even in parallel, and seek for the compiler feedback and aggregate them, and it's going to do a summary of what's happening, and then it's going to planify for next step. So when you have a hybrid model like this, it's going to do multiple tasks. It's called currently the most popular agentic framework. So you use a model who is playing multiple roles to achieve what you want to do. So today, people, it's not like black and white. Well, I mean, this is a debate at the beginning of the year, but today everyone, I believe, is using something agentic to achieve, to do autoformalization. So when you called Aristotle or Gauss behind your API, it's probably an agent which is able to do search, to correct its own proof, and to do a planning for what's going to be next, something like that.
Okay, thank you.
Okay, one last question. Yep.
Hi, thanks for the nice talk. So I just recently tried the LeanDex on my mobile phone. So I have tried to enter 2 to 3 theorems, and it exactly giving the 15th result, like just 15 results of each theorem. Why particularly? Like
the 15 result?
Yep.
What do you mean by the 15 result?
Like I've tried to enter like Fermat's last theorem and some
yes.
basic.
So this is a search engine. I'm not sure I get your question. I'm sorry.
Actually, I choose the packages like Lean and Mathlib and etc. I've chosen the 3 packages, and after I have entered the input like Fermat's last theorem, Pythagoras theorem, exactly it is showing me the 15th result of each theorem. So why particularly 15? Is there?
Okay, yeah. I think it's they have to choose a number, so it's like they are showing the 50 best result. That's kind of what's happening behind. Yeah.
Means there are lots of results of the same. It is particularly showing us 15. That's strange. Like.
Yeah, so it's like what happened is like you send a query, we are going to optimize it, and we use a semantic search, and then we are going to find the most likely result and rank them in according to a certain order. And here, unfortunately, because of the complexity, we only display the most 15 promising one. So that's kind of what happened. I don't know. Is it what you're asking? No.
Okay, I think we can take the discussion to lunch.
Yeah, maybe we can discuss it after a while. I think I'm not getting your question.
So thank you very much for this great talk. Thank you.